Yeah, first of all, I have to say this is still an ongoing work, so we're still lacking some informations, but the results we achieved by now are quite interesting, and this is the reason I want to present it today here. So this whole project was made in collaboration with the TU Bergakademie Freiberg and Hochschule Osnabrück, was part of our project. So what is the motivation of adding aluminium to austenitic steels? And basically I want to come from the conventional processing side in this case. So when we add aluminium in austenitic steels, for sure, we will change the density of our material. So in our research, we will have a look at the aluminium content starting from like 0 amount of aluminium until 6% of aluminium. And if we change this content of aluminium, we will decrease our density of nearly 0.7 gram per cubic centimeter. So this is the total idea, that we can have a lightweight design with a concomitantly increase of strength. So in the S-cast condition, when we start with 0.1 aluminium, we have some kind of a 316L type alloy, and then we have a low yield strength and a high ductility in the end, and some work hardening behavior there. But if we add more aluminium, then mostly we'll increase the strength of our material, and in the end, up to 6% we will lose our total ductility in here. So why would you use these in additive manufacturing? So the idea behind is that we have rapid solidification in additive manufacture, and therefore nano-oxides of aluminium which can be built up in there. Those nano-oxides might be able, as precipitates, to break up the columnar grain probe, and therefore we will have a more fine-grained microstructure, and therefore less anisotropy in our mechanical behavior. So this was basically the idea behind this. And the experiment setup we used for this was a SLM280HL machine, and all those compositions I already explained were printed with the same parameter setup. Due to limited amount of powder, unfortunately we were only able to print in a light down position, so the building direction is perpendicular to our loading direction in the present case. The process condition we were changing was the temperature. As we all know, is the temperature of the build plate crucial for our solidification rate, and the SLM280 is able to have a build plate heating up to temperatures of nearly 800 degrees. Due to safety reasons, it will shut down at 800 degrees, therefore we used 780 degrees. So let's get back to the theoretical background. We saw when we printed a chrome manganese nickel steel with different amount of nickel content that we can have a change of our phase stabilities due to different nickel contents. Starting with 9% nickel, we have basically a 316L type of steel, so grain structure looks like everyone would expect in an austenitic steel, and we are having a fully FCC microstructure. If we decrease the nickel content, then our field of this FCC microstructure will be shortened. So due to rapid solidification, we will still get an FCC microstructure, but due to change in stacking fold energies, etc., in this case, we have already kind of a dual phase microstructure with some epsilon margin site, so the HCP phase in there. So really interesting it is when we go to the 3% nickel content. In this case, we have some delta ferrite up there, and if we print in this condition or print it with the same parameter setting, then we will get some BCC microstructure. The PCC microstructure is intersected by Widmann-Steffen grains in an FCC manner, and we also found the HCP epsilon martensite in there. So basically, those phase maps are crucial for our solidification behavior, although, yeah, you would expect that all those alloys would solidify in an FCC microstructure because, yeah, this field is still huge for the 3% nickel alloy. When we change the process condition, we will change the solidification rate, and this is basically something we see in the microstructure as well. So this is already results for the 0.1 aluminium alloy, and there we have at the process condition of, yeah, room temperature. I called it 20 degrees, although we all know it won't be 20 degrees, it's more likely like 50, 60, 70 degrees in total while you're printing. Then we have some fine-grained micro grains inside here, and also in loading direction and building direction we have not really a texture, it's most likely random texture. If we go to 500 degrees, then we have a more directional solidification. The grains are getting larger, and therefore we get some idea of a texture, but still it's not that high. This will, in fact, nevertheless influence our tensile test. So if we have a look up here, then we see that the change in build plate temperature will also change our yield strength and ductility. The ultimate tensile strength is not affected by the difference in grain size or texture in here, but with an increasing build plate temperature, our yield strength will drop and the ductility increases in there. Nevertheless, of the process condition, we are much better than cast condition with a totally high strength, but the work hardening rate is changing in here. If we add now some aluminium, then I brought here some microstructure of the 20 and 780 degrees condition. So basically in the 20 degrees condition, we have a grain morphology which is similar to the 0.1 aluminium alloy. So the addition of 1.5 seems to change nothing. Due to the higher temperature, 780, in comparison to the 500 degrees condition before, we have a prevailing texture in here. And in the tensile test, basically, it's the same effect we had before. So 1.5% of aluminium doesn't change anything at all. Unfortunately, I'm showing you the microstructure at 780 degrees. We were testing those samples as well, but as you all know, something shit happens. So we had a lot of porosities in there, and therefore, yeah, the defect tolerance is not there anymore, and our specimens have loss in strength and ductility due to those porosities, and we have to reproduce those samples again. Therefore, those were excluded from the further idea because, yeah, those results were not able to be repeated. If we go to 3 aluminium content, so another 1.5 addition, basically it looks kind of the same. We have in the 20 degrees condition larger grain sizes. So the grain sizes are approximately the same. They are later on in the 780 degrees condition. So therefore, we seem to have like a kind of an effect on our alloy. And for sure, texture is changing again. And the effect on our tensile curves are the same as we saw before. So basically, the yield strength drops. UTS is not changing, but in contrast to the 0.1 aluminium alloy, the total trend in ductility is not that much. So this might be a reason of porosities as well, as you know, when we raise our temperature up to nearly 800 degrees, the whole temperature field and temperature input will change. So there might be an effect of porosities as well, although we didn't find it. So it would be part of our future work to check our samples via micro-CT and so on. If we add 4.5 aluminium, then finally we get the effect we were waiting for. So please mind the different scale bar up here. So we have right here a really fine-grained microstructure, and the microstructure is really depending on the temperature of our build plate. So in the 20 degrees condition, we have some larger grains in there, nevertheless still fine-grained, but they will get really fine-grained in the 780 degrees condition. And this effect will totally affect our tensile tests, and this is the reason I say that this is still ongoing work. There are a lot of tensile curves still missing in there, but we see at 780 degrees we have a strength of more than 1,400 megapascal. The 20 degrees condition has a higher ductility and high strength totally in there. What is the reason for this? Basically, if we take a look at our phases, then we have at the 20 degree condition BCC plus FCC dual phase microstructure. The FCC is responsible for the ductility in here, and at 780 degrees we will have a BCC microstructure here. The 6 aluminium alloy was kind of difficult to process because due to the mainly BCC microstructure here, we have some cracks starting in here. We made some tensile tests, but they failed at 0.1 or 2%, so no more words needed about this. But also here we have like this dual phase microstructure prevailing. If we compare now those different alloys between each other, it's kind of interesting that the 0.1 aluminium and the 3 aluminium alloy are the same about the yield strength. So the yield strength is not really changing, but what will change is the ultimate tensile strength. So in fact, the work hardening rate of our alloys will change up here. The reason for this is that in case of the 0.1 aluminium, we will have some twinning and therefore some dynamic Hall-Patch relationship, which will increase our work hardening up here. The 4.5 aluminium is totally different, as you already saw, just to mark it up here. And the main reason behind this is basically the different solidification behavior. We have some carbides in there, so there's a lot of stuff to do in the phase diagram. We will still have a lot of conditions we have to look at, but mainly the alpha plus gamma microstructure the reason for this. When we compare this to our as-cast condition, I just took the 20 degrees samples for no specific reason. So the specimens which were built at 20 degrees, and we saw in all cases that we have an increased strength in comparison to our as-cast condition. The fully austenitic samples, they don't have a loss in ductility in there, but we see this in case of the 4.5 aluminium condition. The main reason behind this is the dual phase microstructure, and therefore we basically can conclude that our aluminium content is the crucial idea where we have to say that this will change our phase stability. If we change the phase stability, then we have a high sensitivity of our build plate temperature to our microstructure, and therefore we will get different results, and therefore for sure different quasi-static mechanical properties. So therefore I want to thank the Deutsche Forschungsgemeinschaft for the funding of the research. I'm happy to take some questions.